Namaste and welcome to this lecture on mathematical foundations for machine learning. We were looking at probability ideas and we started off with random variables and we looked at discrete random variables. We discussed like why do we need random variables, then we discussed like what are discrete random variables, what are continuous random variables. We just had the definition and then we had the idea of some standard discrete random variables. Like we started off with a single trial 2 outcome random experiment where we tried to model the probability of success, or where we tried to model one success. The random variable is going to look at the number of successes in a single trial, and that is associated with basically a probability p. That means the probability of success is p in single trial. And then we said that okay, you have all these yes no true false 1 0, then male female, then you have success failure, all these things, all these experiments can be put under Bernoulli trial, and then we were trying to model the probability of success in a single trial. Towards the end of the class we also had a couple of questions. We said look, that is fine, one trial, okay, I know what is the probability of success and what is the probability of failure. Now I am not interested in just one trial, I want to play this game which has a win or a loss to be the result. I want to play this game, let us say 10 times, and in that 10 times I want to model k number of successes, right. I want to model k number of successes in 10 trials. So the question that I ask is, in 10 trials what is the probability of getting 7 successes, or let us say 8 successes, right, probability of team A winning 8 times in a game in a series of 10 matches. So I want to look at that, and that is exactly what we are going to do with what we call as the binomial distribution or the binomial random variable. So let us look at that now. So what are we going to do? We are going to look at repeat Bernoulli trials n times. So the question we ask here is, what is the probability of k successes in n trials, right, in n trials. This is the question that I have. Let us take a simple thing like what we did in the previous classes, where we tossed a coin 3 times, and in 3 times I want to model 1 success and 2 successes and so on. So let us look at this example. So consider tossing a coin thrice. Let x denote the number of successes, and we will also define what a success here is, number of successes, namely the number of heads. In 3 trials. So we are going to have 3 coin tosses, going to look at the number of successes. I want to find out what is the probability of getting, let us say 2 successes, or probability of 1 success, 0 success and 3 successes. I want to look at that. Let us take this case. So the random variable x can take values 0, 1, 2 or 3. So 0 corresponds to, let us say, the outcome tail tail tail. So I am going to look at 3 tosses, in all 3 tosses I get tail, then I am going to have head tail tail, tail head tail, tail tail head, then 2 is going to be this head head tail, head tail head, tail head head, and the 3 games and all the 3 giving me heads, 3 successes I am going to have this. Now if you look at this, let us look at this and this, then we will see, we will try to understand this better. So what do I have? In 3 trials I can have the first success. If I am just talking about one success, the first success can come in the first trial or the second trial or the third trial. Suppose if I want to look at 2 successes, 2 heads can come in the first 2 trials, or it can come in the first and third trial, or it can come in the second and third trial. That means if you look at in these 2 cases, there is something interesting that is happening. What is that? If you look at x is equal to 1, I have 3 choose 1 ways of getting 1 success in 3 trials, right, ways of getting 1 success in 3 trials. And similarly I have x is equal to 2, I see I have 3C2 ways of getting 2 successes in 3 trials. Okay, I can also look at x is equal to 0, x equal to 0 corresponds to 3C0 ways of getting 1 success, getting 0 successes in 3 trials, and I have x is equal to 3, which is basically 3C3 ways of getting 3 successes in 3 trials. So what do I have? I want to look at this. So I want to look at probability of x is equal to 2 in 3 trials. This is nothing but 3C2, and I look for 2 successes, which means I am going to have p power 2, and there is one failure which is going to be 1 minus p, precisely what we see here. Success with a probability p, success with a probability p, it is p into 1 minus p, p into 1 minus p into p, 1 minus p into p, that is what we have. So we have 3C2 p power 2 1 by into 1 minus p. Similarly I have p of x is equal to 1 is nothing but 3C1 p power 1 into 1 minus p the whole squared, and I have p of x is equal to 0, which is nothing but 3C0 p power 0 into 1 minus p the whole power 3, and p of x is equal to 3 is nothing but 3C3 p power 3 1 minus p power 0. Therefore what I see is, whenever I am looking for k successes in n trials, I am going to look at this, the probability mass function of k successes in n trials, I will say in n Bernoulli trials, because I am still dealing with only 2 outcome experiments. I am going to have p of k successes in n Bernoulli trials is given by probability of x is equal to k is equal to n choose k, like what we had here 3C2 n choose k, k successes we want, so it is p power k into 1 minus p power n minus k. And what are the values k can take? K can take values from 0, 1, 2, maximum it can go till only n. You play 10 matches, maximum you can get only 10 successes, 0 otherwise. So this is the probability mass function of k successes or a Bernoulli or a binomial random variable, where the binomial random variable is going to look at, or it is going to model k successes in n trials. So, I am going to say x is binomial of k, binomial of n number of trials, comma the probability of success is basically given by p of x equal to k. The probability mass function is n choose k p power k 1 minus p power n minus k, k is equal to 0 1 2 n 0 otherwise, right. This is the probability mass function. Okay, great. Let us see something interesting here. Let us just take, we are looking at anyway an experiment with 2 outcomes, multiple trials of that. So, I will do something here. Consider the consider the random experiment of choosing let us say red card from a well shuffled pack of 52 cards. Okay, I will just say consider the random experiment of choosing a card from a well shuffled pack of 52 cards. Now, I am going to define what is success and what is failure. So, success is basically, success corresponds to picking a red card, and failure corresponds to picking a black card. Right. So, I give you a pack of a well shuffled pack of 52 cards. We know that in a pack of 52 cards we have 26 red cards and 26 black cards. Now, therefore, the probability of success in this case, probability of success is equal to probability of choosing a red card which is equal to 26 by 52, right, just 26 by 52, and probability of failure is equal to probability of choosing a black card, which is also equal to 26 by 52, right, it is also equal to 26 by 52. Now, so what I do is I shuffle this, I shuffle this pack of cards again, and then I give you this well shuffled pack of cards. Now, what I do is I ask you this question: what is the probability of a success in this particular trial? The first trial that I am going to do, I am going to shuffle a pack of 52 cards with 26 red cards and 26 black cards, and I am going to give it to you. Now, I ask you the question: what is the probability of getting a success? That is pretty obvious. You say it is 26 by 52 because you have 26 red cards out of 52 cards. So, the probability of success is going to be 26 by 52, and then the probability of failure is 26 by 52. Now, what you do is I give you the pack of cards, you pick up a card, you see that it is red, it is a success. Now, what I do is I keep that red card out. Then what I do, I again shuffle, and then I give you this well shuffled pack of 51 cards, and then I ask you what is the probability of success in this pack of 51 cards. Something interesting happens here. What is that? Initially the probability of success before I put that card out was 26 by 52 and 26 by 52. Now I got a red card, you drew a red card from it, you kept that card outside, and then I gave you the well shuffled pack of 51 cards. You find something interesting happening. What is the probability of success now? It has gone down from 26 by 52 to 25 by 51. That means what was 50% success chance has now gone down to less than 50% success chance. And what about failure? The chance of a failure, it has increased, it is still 26 by 51, which is slightly more than 50% chance. So you have probability of success in the second trial was basically 25 by 51 and probability of failure was 26 by 51. I show you this pack of cards. Wow, you are second time lucky, you pull out another red card, I keep that red card out. Then again I shuffle the cards and then I give it to you. Third time, third trial. In the third trial now I ask you, what is the probability of getting a success? It has come down now to 24 by 50, which is much less than 50%. And what about the probability of failure, probability of getting a black card? That is still 26 by 50, which is much more than 50%. Third time you are lucky, you pull out this card, keep it out. Now what is happening here, if you see that as and when I pick the card and then keep it out, I end up getting the probability of success to change from trial to trial. That means the outcome of one trial is trying to influence the outcome of the other, right, because at some point of time you will run short of all those red cards because I put all my red cards out, which means all these outcomes are actually affecting the trial, they are all affecting the trial, in which case the probability of success from one trial to the other trial keeps changing, and the outcome that you have got in each of those trials is trying to influence the outcome of the other. That means the probability distribution does not remain the same. If it does not remain the same, we have a problem. We have written our binomial distribution as n choose k p power k and 1 minus p power n minus k. We have written this. Now what happens in the first trial, the probability of success was, let us say 50% 0.5 and the probability of failure was 0.5. In the second trial, p changed from 26 by 52 to 25 by 51 and 1 minus p still remained as 26 by 51. That means this probability changes. Therefore whenever we have this kind of a problem, that means we look at Bernoulli trials wherein which the probability of success and the probability of failure across trial keeps changing, it is not the same. Why did that happen? It happened because you took the card and put it out, you did not put back the card into the pack. If you had whatever the card that you have chosen, if you had put it back to the pack of cards, then the probability would remain the same. Instead what did we do? We drew a card out, we saw the color and then we kept the card out of the pack, which means the probability distribution now changes across the trial, it changes. Therefore this whatever that we have written here would not work if the probability of success and the probability of failure keeps changing across the trial. That means this would not work if the outcome of one trial is going to influence the outcome of any other trial. That is a problem, and this is exactly what you would have learnt in your high school as sampling without replacement. What do? Take a well shuffled pack of cards and pull out a card, see the color, keep the card outside. This is what we would have done in your class 10-11 probability course as sampling without replacement, in which case the success probability and the failure probability keeps changing across the trial because you keep the card out. But what we are looking for is the probability of success and the probability of failure to be the same across all the trials, because you are running n trials, across all the n trials, the probability of success and failure should remain the same, only then this would capture that particular phenomenon of the probability of success and failure remaining unchanged. So what we want is, we want to look at what you studied in your class 12 as sampling with replacement. That means you pick the card, see the color, put the card back to the pack, and then you take the second card, you shuffle the cards, pick the next card, you see something, I mean you observe the color of the card, put it back. Now whenever you put the card back, the probability of success and the probability of failure remains the same, it does not change, right, it does not change. Therefore, whenever we talk about binomial random variable, it is not that the trials must be just successive Bernoulli trials, but it has something more to it. I do not want this probability of success p and the probability of failure 1 minus p to change. I do not want them to change, I want them to remain the same across all the trials. So how do we do that? That is exactly where we get into the notion of independent and identically distributed random variables. So what we say is independent okay, so we are going to say there is a condition that we are going to put here, we will change this, we will say probability of k successes in n independent and identically distributed Bernoulli trials, identically distributed Bernoulli trials. If they are not independent and identically distributed, then this would not work, where the probability distribution keeps changing, this would not work. The probability distribution of success and failure must remain the same across all the trials, and the outcome of one of the trials should no way be influencing the outcome of the other. So that is what is called as independent, and the distribution being the same says it is identically distributed. So what are the conditions for you to model a random variable as a binomial random variable? We have this. So we say x is binomial of n comma p, that means n trials with probability of success p. See, that is exactly why this must remain the same, this should not change. Binomial of n comma p is basically, it requires the following. This implies, number 1, it is associated with experiments with just 2 outcomes, random experiments with 2 outcomes, random experiments with 2 outcomes, then finite number of trials, let us say n. Third, probability of success is p, failure probability is 1 minus p. Number 4, trials must be independent and 4, the probability distribution, we will see what this probability distribution means in the next class, but then we will just write it down. The probability distribution of success and failure must be identical okay, let us say failure across the trials must remain the same. Identical. So, in essence what we are saying is we want to look at sampling with replacement and IID, basically independent and identically distributed. This you will come across in multiple places, independent and identically distributed. Right. If that is the case, if all these things work, then my probability mass function is given by P of x is equal to k is given by n choose k p power k 1 minus p the whole power n minus k, k is equal to 0, 1 etcetera n 0 otherwise. Right. This is basically the binomial distribution. Remember in the previous class when we did, we also had a second question for which we tried to find the answer. What was the second question? What is the probability of the first success in the kth trial? That means k minus 1 trials or failure. So, what is the probability of the first success in the kth trial? Let us look at that. We want to answer this question too. So, the question we are going to answer is, suppose we have a Bernoulli experiment is, as I said, it is a random experiment with just 2 outcomes with probability of success p and failure probability being 1 minus p. We have a Bernoulli experiment. We want to know what is the probability of the first success occurring at the end in the nth trial. What is the probability of success of the first success in the kth trial. Right. I am quite sure now you are witnessing, let us say, the 18th edition of, let us say, the Indian Premier League cricket match, and there are certain teams which haven't yet made mark by winning the trophy even once. So, now I am going to ask you this question: what is the probability of so and so team winning the trophy, IPL trophy, for the first time in the 18th edition? That means all 17th edition, all 17 editions have been a failure. What is the probability of this particular team winning the IPL trophy in 18th edition? Right, this is the question I am going to ask. Therefore, I also have another constraint here. What is that? It is not that I am looking for the first success in the kth trial. Suppose I win this particular team, let us say if it wins in the 18th edition of this IPL, now what we do is we say that okay, we stop playing. It is like for any of us, like when we write an exam, you do not pass in the first attempt, you take it the second attempt, you do not pass in the second attempt, you take the third attempt, you try to clear the exam, you try to write the exam till you clear for the first time, because once you clear you do not have to write the exam again. So, this is the condition that I have. I will play as long as I register my first victory. Once I win the first time, I stop playing, which is exactly what we do in our exams and stuff. So, now I ask you the question. That means there is another interesting stuff. What is it? I am looking for my first success. Suppose I get the first success in the first trial, I do not play this game at all anymore. First time I have got a success, therefore I stop playing. Suppose I do not get a success, therefore the first trial would be a failure. The second trial I could get a success. Now if I get it in the second trial, I stop playing the game. I do not get failure, I mean I do not get a success in the second trial also, therefore I will play the third game. If I succeed in the third game, I stop, otherwise I continue to play till I register my first success, right. It is like saying arise, awake and stop not till you succeed, right. You keep playing the game till you succeed. Once you succeed, stop playing the game, do not play it again. It could be so like in our current context where I was talking about, let us say IPL, where this team, let us say it keeps playing till it registers the first success. Suppose if they say okay, we are waiting for the first success for this particular team to happen, I could as well say that okay, after the team registers the first success, let us say there is going to be no more IPL. It is a very hypothetical situation that I am talking about. So the thing is, I want to know what is the probability of this particular team winning the trophy at the 18th edition. I want to model that, right. Here again you see, here again it is Bernoulli trial, that means it has probability of success and probability of failure, and we are repeating the trial again and again till we register the first success. Therefore the probability of success and failure should not change across the trials, it must remain identical. That is what we said, the distribution must remain identical, and whether I mean the result of the 17th edition or the result of the 16th edition is no way going to influence the result of 18th edition. Every game is played a new, I mean it is a start from the first, right. Every game is a new game, therefore you do not say that we have lost in the previous 16 editions or 17 editions, therefore all that results get accumulated here. Now I am going to look at the success based on those 17 editions. No, I am not going to talk about that at all. Every game is new, that means the outcome of the previous editions of IPL is no way going to influence my current outcome, the outcome of the current edition of the IPL that is happening. Now I want to model this, I want to model the probability of first success in the kth trial, meaning if I register the victory in the kth trial, I stop playing after that, because I have got my first win, I will stop playing the game after. That is the condition that we are going to look at. So what is the random variable which will model the first success in kth trial, and that is exactly where we get into the idea of geometric random variable. So I say x is geometric distributed, geometric random variable with probability of success p. Right. So what is the probability of the first success in the kth trial? So what does this mean? I am looking for the probability of the team winning the title for the first time in the kth trial. Right. This is given by, what is that? If it is k trials, I already had k minus 1 failures and success at kth trial, right. Now what are the values that k can take? K definitely you cannot say okay walk over without playing the game, 0 games played, you cannot do. So k minimum starts with the first, k is equal to 1, 2, and what did we say? We said arise, awake and stop not till you succeed. That means you keep playing the game till you register the first success. So keep going on. Therefore countably infinite. This is exactly what we saw in the first lecture on the random variable, where we said go stand in a signal and then count the number of vehicles that pass through the signal. You could have a countably infinite number of values, and that is exactly what we see here. K is equal to 1, 2, etc. It goes till infinity and 0 otherwise. So, a geometric random variable basically models the first success in the kth trial, right, and the requirement is you stop playing the game after the kth trial. I mean, when you register the first success, and the probability of success and failure must remain the same across all the trials, and outcome of no trial is going to influence the outcome of any other trial. So, it is similar to binomial, except that in binomial you play the game for a finite number of times, and in that you count the number of successes. In geometric we are going to look for the first success, we are going to play till we achieve the first success. That means if it comes to infinitely many trials, keep playing, that is what it is. So, the requirement here again we have, the requirement is that the probability distribution of success and failure, or probability distribution success and failure when I say probability distributions, it is basically this p and 1 minus p that we have, it must remain unchanged, it must remain the same throughout, I mean for all the trials, right, must be identical across trials. And trials must be independent, that means trials, the outcome of trials must not be influencing the outcome of other trials. So, trials must be independent, and the most important thing is keep playing the game, keep playing till the first success is registered. Stop at the first success, that is it, stop playing at the first success. So, this is basically the geometric random variable which has this probability mass function as given above, right, as given here this. Now, it is interesting because in all the 3 random variables that we looked at, we were more worried about random experiments which just had 2 outcomes, success and failure. So, the question is, can we have multiple outcomes, like how you had the random experiment of rolling a die which had 6 outcomes, right. Now, what could happen there? So, that is exactly where we get into the idea of what is known as, I mean we are just going beyond these 2 outcomes. So, I am going to look at a very important discrete distribution which is basically called as the equally likely random variable, equally likely distribution. So, I will say x is, let us say, equally likely of n. Now, what does this mean? I have the range of x to have n values, let us say x1, x2, etc., let us say x n, let me put it this way, n caps, x is equally likely with n values. Now, what does this mean? This implies probability of x taking any xi is equal to 1 by n, I have n values. Now, what does this mean? This simply means, okay, let us do this, for xi is equal to x1, etc., xn. What does this mean? This simply means the probability of choosing any fellow from this set is the same as the probability of choosing any other fellow in the set, or is the same as the probability of choosing every other fellow in the set. So, that is what is equally likely distribution. For example, many of us, when we ask what is the probability of getting a head in a coin toss, we end up saying that the probability of getting head is 1 by 2 and probability of getting the tail is therefore 1 by 2. Now, if that is the case, there are two outcomes that we have, both outcomes are equally likely, that means they have the same chance of occurrence. So, you call that as equally likely distribution, right. So, that is basically what we call as equally likely distribution. It is also called as the discrete uniform distribution, or it is also called the discrete uniform distribution. Right. The other one that we have, one more let us say one more discrete random variable, we have what is called as the Poisson distribution. We say the random variable x is Poisson distributed with parameter lambda. We say it is with parameter lambda. We will see what this is. This basically Poisson distribution or a Poisson random variable basically models the number of arrivals for example, there is a shopping mall, I want to find out what is the number of customers that arrive at this particular shopping mall in a given interval of time, knowing well that this is the average number of customers that they go. So, where lambda is basically the average arrival rate. So, let us put this. So, I will write the expression and then put this explain all these terms. It models the number of arrivals, it could model the number of web page hits, the number of web page hits, it could also model the number of typographical errors in a sheet of paper, typographical errors, etc. It could do a lot of stuff. This all these things are model using Poisson distribution, where the probability mass function, this is the PMF of equally likely, and we have the probability mass function of x which is Poisson distributed is given by probability of x is equal to r. That means r arrivals in a given time interval is given by e power minus lambda, lambda to the power of r by factorial r, r must be greater than or equal to 0. So, I would say r, since it is number of arrivals, it is going to be a countable guy. So, I am going to have r is equal to 0, 1, 2, etc. infinity, right, where I am going to say this lambda is basically the average arrival rate. And the average arrival rate, and this fellow is greater than 0, right. It is the average arrival rate which is greater than 0. We will see this in detail a bit later, but right now what we have done is till now we have seen a lot of discrete random variables, basically the ones with just 2 outcomes. We could do 3 things with those 2 outcome experiment. One is conduct the experiment only once, model the probability of success. The second was conduct the experiment for a finite number of times, try to model the number of successes in that finite number of times. The third one was very important, where we said, look, I want to find out what is the probability of getting the first success in a kth trial, and we said that keep playing till you get the first success, stop playing after you get the first success. So, we looked at Bernoulli random variable, binomial random variable and geometric random variable. Post that we asked the question like, is it always that you just have two outcomes experiment, we just have two outcomes and then you can model success and failure? We said that no, we can actually have multiple outcomes, in which case we ended up getting equally likely distribution, I mean multiple outcomes with each outcome having the same probability mass function or probability mass value. So, we said that the probability of choosing any element from the set is the same as the probability of choosing any other element from the set. That means each fellow is going to be as equally likely as the others. So, we had this equally likely distribution or the discrete uniform distribution. Then the other one that we wanted that we looked at is like, I want to model the number of arrivals in a particular place. It could be a shopping mall, it could be a theater, it could be anywhere. I want to model the number of arrivals, and that is done using our Poisson distribution with a parameter lambda, where lambda is called the average arrival rate. Now, these are the standard or very most common or very important discrete probability distributions or discrete random variables that we have. We have a lot more, and so what we do is we know that the discrete random variables are basically characterized using probability mass function. We have seen some properties of probability mass functions and so on. When we come back for the next lecture, we will end up looking at continuous random variable, because whatever we have done here in terms of probability mass function is not going to work there. The reason being, the random variable is defined over a continuum or over an interval which has uncountably infinite number of points. If that is the case, how do we handle it? So, when we come back in the next lecture, we will look at continuous random variables, and then we will start looking at modeling a random variable through something else. I mean, till now we looked at probability mass function as a model for the discrete random variable. We said that it is not going to work for a continuous random variable, therefore I have to look for something else to characterize a continuous random variable. We will see what that is. Now, we will take some scenario where you will not be able to get either this or that. In that case, how do I model a random variable? I would not know the distribution of the random variable. So, how do I model such random variables? That is the focus of the next couple of lectures. We will look at expected values and variance and a whole bunch of stuff in the next lecture. Namaste.